I want you to do something for me right now. Wherever you are, sitting on the train, walking the dog, or just lying on the couch, I want you to wiggle your big toe.
Go ahead.
Just give it a little twitch.
It seems incredibly trivial, doesn't it?
It does. We do it thousands of times a day without, a single conscious thought.
Exactly. It feels instant. It feels simple.
But if we actually hit pause on reality for a second
Mm.
and look at the engineering required for that one little wiggle, it's just absolutely mind-bending.
It really is. You have an electrical signal that starts up in your brain in the motor cortex.
Right at the top.
And it has to shoot down the spinal cord, exit through a nerve root, and then, this is the part that always gets me, it has to travel down an axon that is just, well, the scale is astronomical.
The scale is the whole story here, isn't it?
It's a scale issue that is so hard to comprehend. We tend to think of cells as these microscopic little spheres, but a motor neuron is a completely different beast.
Not a sphere at all.
Not even close. If the cell body, the perikaryon, the factory where all the proteins are made, if that was the size of a tennis ball,
Okay, I'm picturing a tennis ball in my hand.
then the axon, that single wire carrying the signal, would stretch for something like a mile.
A mile.
Yeah.
That's incredible. A mile-long wire being maintained by a tennis ball.
That is the architecture we are dealing with,
Yeah.
and that's the source of its vulnerability.
Precisely. And that wire has to be perfectly insulated. It has to traverse moving joints and compress tunnels in your wrists and ankles.
It has to jump a chemical gap at the very end, and then finally it has to trigger a biological engine, the muscle, to contract.
And it has to do all of that in a fraction of a second.
Flawlessly, thousands upon thousands of times a day.
And that entire chain, from the decision in your brain to the actual wiggle in your toe, it relies on two fundamental concepts that we are going to explore today.
And what are they?
Continuity and energy.
Continuity and energy. That's a perfect summary. The wire has to be unbroken and the engine needs fuel.
Because when that connection breaks, or when the engine runs out of power or breaks down structurally, that is when we see disease.
And that is the core of our deep dive today. We are looking at Patho 27, peripheral nerves and skeletal muscles.
And to guide us through this complex wiring and this incredible machinery, we are synthesizing two absolute powerhouses of pathology. We've got our guidebooks, as we like to call them.
We do. First up, we have Robbins and Cotran. It's essentially the encyclopedia of pathology.
Says the Bible.
It gives us the breadth, the classifications, the what does it look like under a microscope details. It's the map of the territory.
And then we have Underwood.
Yes, Underwood. I love Underwood because it gives us the mechanism. It's the how and the why. It explains disease not as a static list of symptoms, but as a dynamic response to injury.
So Robbins might tell us this is a traumatic neuroma.
Exactly. But Underwood explains this is why the nerve got confused and tangled up in the first place. It gives us the story behind the lesion.
A perfect partnership. And quick disclaimer before we jump into the weeds here. This deep dive is an interpretive synthesis.
A conceptual map.
Exactly. We are giving you the framework, the stories, the connections. But you still need to go back and read the chapters. We are the tour guides. We aren't the terrain itself.
Think of this as the scaffold you build before you lay the bricks of detailed memorization. Reading is still essential.
So our mission today is pretty specific. We want to move beyond just memorizing a list of, frankly, terrifying muscle diseases. We want to understand the mechanisms of failure.
And that failure almost always comes down to a central tension in the human body.
Which is?
The extreme vulnerability of a peripheral nervous system because of its immense length and the absolute structural dependence of the muscle on that nerve.
It's a relationship.
It is a very codependent one. If the nerve goes quiet, the muscle withers. It's called denervation atrophy. The muscle has no purpose without the signal.
And like many relationships, if communication breaks down, things get ugly fast. So let's start with part one, the wiring.
The peripheral nerve structure and function. Let's get into the nuts and bolts.
Let's unpack the anatomy of this connection. We mentioned the neuron. I always picture it as a factory.
That's a very accurate analogy. The cell body, or the perikaryon, is the factory. It sits safely tucked away in the spinal cord or right outside it in the dorsal root ganglia.
Protected by bone.
Exactly. It's the command center. It's where the nucleus is, where the proteins are made, where the metabolic decisions happen.
And the axon is the delivery truck. Or maybe the supply line?
The axon is the transport line. But calling it a line really diminishes the scale, doesn't it? Remember that tennis ball and the mile-long wire?
Right.
The metabolic challenge here is immense. The factory has to synthesize, structural proteins, enzymes, organelles, and then physically transport them down that mile-long tube to the very tip of the toe.
And that transport is an active process. It's not just stuff diffusing down.
Oh, not at all. It's a two-way highway system called axonal transport. There are motor proteins, kinesin and dynin, that are literally walking along microtubule tracks carrying cargo.
Like little microscopic trains.
That's a great image. Kinesin carries things away from the cell body, and dynin brings the waste products and signaling molecules all the way back up.
So if there's a supply chain issue in the factory or a road closure on that highway,
The end of the line, the toes, the fingertips, are the first to suffer. That's a theme we'll see again and again.
that makes perfect intuitive sense. Now, this line isn't just a bare wire. It's insulated.
Right. And this is where the Schwann cells come in. In the peripheral nervous system, the Schwann cell is the dedicated caretaker of the axon.
Its job is to create myelin.
Yes, it wraps itself around and around the axon like rolling up a sleeping bag to create this fatty sheath called myelin.
And Robbins makes a really specific distinction here about how they wrap, how it's different from the brain, right?
Nice. A crucial distinction. In the brain, the central nervous system, you have a cell called an oligodendrocyte. And it's kind of like an octopus.
An octopus, I like that.
It can reach out its tentacles and wrap multiple axons at once. Very efficient. But in the peripheral nervous system, the PNS, the Schwann cell is, well, it's monogamous.
One Schwann cell, one axon segment.
One Schwann cell creates exactly one segment of myelin. We call that segment an internode.
So if you look at a nerve under a microscope, it's like a string of sausages.
That's the classic description. Each sausage is a segment of myelin made by one Schwann cell, and the tiny little gap between them is the node of Ranvier.
And that's where the magic happens. The signal doesn't crawl, it skips over the sausages.
That's saltatory conduction, from the Latin saltare, to jump. The electrical signal, the action potential, doesn't have to propagate down the whole wire. It regenerates and jumps from node to node.
Which makes it incredibly fast.
Massively faster. Without myelin, we'd be moving in slow motion. Our reactions would be hopelessly slow.
So we have the factory, the long transport line, and the insulation. But these nerves act in bundles, right? They aren't just floating around alone in our limbs.
No, absolutely not. They are packaged very, very carefully in layers of connective tissue.
Okay, break that down for us.
You have the endoneurium, which is a delicate layer around each individual myelinated fiber.
Endo meaning within.
Right. Then you have the perineurium, which bundles groups of fibers into fascicles. And the perineurium is really important. It forms the blood-nerve barrier. It's a very tough, protective layer.
Like the plastic casing around a bundle of wires inside a big cable.
A perfect analogy. And then the whole nerve cable, with all its fascicles, is held together by the epineurium on the outside.
It's industrial cabling. But even industrial cables get damaged, they get cut. So let's talk about what happens when things go wrong. Mechanisms of nerve injury.
There are really three main ways a nerve fails, and understanding these three patterns unlocks almost all of neuropathy.
Okay, what's the first one?
The first is the most dramatic. It's what happens when you physically cut the wire. We call this Wallerian degeneration.
This is the trauma scenario. A knife wound, a bad fracture that severs a nerve, a saw accident.
Exactly. Imagine you sever that transport line. The cell body is fine. It's way upstream, safe in the spine, but the line is cut.
So everything downstream is cut off.
Everything distal to that cut is now separated from its source of life, from the factory. It's an orphan.
So dies.
It degenerates. The axon itself breaks down into fragments because it's not getting any new supplies, and the myelin, which can't survive without a healthy axon, unravels.
And this is where Robbins describes those myelin ovoids.
Yes, they're basically these little spherical tombs of disintegrating myelin and axon debris scattered along the path where the nerve used to be.
That sounds grim. Who cleans up the mess?
That's the job of the macrophages, the cleanup crew of the immune system. They come in and they phagocytose, they eat the debris.
But here's the miracle of the peripheral nervous system, which is so different from the brain and spinal cord.
It really wants to regenerate. It has an incredible capacity for repair.
So the factory can rebuild the line.
It can. The Schwann cells that lost their axon don't die. They actually proliferate and align themselves into a sort of guide path called a Bungner band.
A Bungner band. So they're creating a tunnel for the new nerve to grow through.
Precisely. The axon from the proximal healthy stump begins to sprout, sending out little feelers. And hopefully one of those sprouts finds the entrance to that Schwann cell tube and starts to grow down it.
How fast are we talking? Is this a quick process?
Not at all. It's painfully slow, about 1 to 2 millimeters a day.
Wow. So if you sever a nerve in your shoulder, it could take a year, maybe more, for it to reach your hand.
If it makes it at all. And that is the big if. This regeneration only works if the two cut ends are lined up perfectly, if the gap isn't too large.
What happens if they aren't? What if the surgeon didn't get them perfectly approximated, or if the trauma was just too messy?
Then the sprout misses the tube. The axon keeps growing because that's its program, but it has nowhere to go. It gets tangled up with the Schwann cells and scar tissue in a big, messy ball.
And that is a traumatic neuroma.
Exactly. And Robbins describes the histology of this beautifully. It's a haphazard swirl of axons, Schwann cells, and connective tissue. A disorganized mess.
And clinically, what does that feel like for the patient?
It's a painful, exquisitely sensitive lump. If you just touch it, it can feel like an electric shock.
Why?
Because those are live, confused nerve endings that are firing inappropriately. They're meant to be connecting to a muscle or a patch of skin, but instead they're just trapped in scar tissue.
Ouch. Okay, so that's the cut wire. What about when the wire is fine, but the insulation is bad?
That is our second mechanism, segmental demyelination.
So the axon is intact. The copper wire is fine.
The wire is intact, but the Schwann cells, the insulation, are either attacked by the immune system or they fail because of a hereditary defect. They're stripped off the axon.
So the signal slows down or just stops. That saltatory conduction, the jumping, can't happen.
It can't. The signal fizzles out, but the body, again, tries to fix it. The remaining Schwann cells divide and wrap new myelin around the bare axon.
But is this repair job as good as the original?
No, it isn't. The new segments of myelin, the new internodes, are shorter and thinner than the originals. It's like a patch job.
And if this happens over and over, if the insulation keeps getting stripped and repaired,
that is where it gets really interesting visually under the microscope. This is where Robbins talks about onion bulbs.
Onion bulbs, that's such a specific and memorable image.
It's perfect. Imagine concentric layers of Schwann cell processes wrapping around and around the axon, trying to protect it, layer upon layer. If you cut the nerve in cross-section, it looks exactly like the layers of an onion.
So if you see an onion bulb on a biopsy, you know this nerve has been fighting a chronic battle for a long time.
Exactly. It is the histologic hallmark of chronic demyelinating neuropathies, like Charcot-Marie-Tooth or CIDP. It represents a history of injury and repair.
Okay, so we have our third mechanism. We've had the cut wire, which is Wallerian. We've had the stripped wire, demyelination. What is the dying back?
This is axonal degeneration, and Underwood has a fantastic term for it. Distal axonopathy.
Axonopathy. So the disease is in the axon itself.
Right. Go back to our factory analogy. Suppose the factory is under metabolic stress, maybe from a toxin, a lack of key nutrients, or most commonly from diabetes. It just can't produce enough energy and materials to support the full length of that mile-long line.
So it has to make a choice. It cuts off the furthest outposts first to save the core operations.
Precisely. It pulls back support from the most distant points. The nerve begins to die from the toes upward, from the fingertips inward.
And that explains the clinical pattern we see in so many people.
The classic stocking and glove pattern.
Right. Numbness and pain starts in the toes, it creeps up the legs to the knees, like putting on stockings, and then later it starts in the fingertips and moves up the hands, like putting on gloves.
And it's not random, it's pure geometry. It's because those are the longest wires, the ones with the highest metabolic demand. It is a length-dependent failure of the factory supply chain.
That is such a clear way to visualize it. So we have the mechanisms. Now let's look at how these show up in patients. Part 2, patterns of neuropathy.
We can classify these by geography. Where is the problem located?
First up, the simplest one, mononeuropathy. Mono meaning one nerve.
This is usually a physical, mechanical problem, compression or entrapment. Carpal tunnel syndrome is the absolute poster child here.
Right, the median nerve gets squashed under the transverse carpal ligament at the wrist.
And because it's the median nerve, you get numbness and tingling just in the thumb and the first 2.5 fingers. One nerve, one specific predictable territory.
Simple enough. But then there's this term that always used to confuse me. Monogeritis. Multiplex.
It sounds like a real mouthful.
It does. It sounds contradictory.
But if you break it down, it makes sense. Mono means single nerves are affected. Multiplex means multiple of them. But the absolute key is that they are random and non-contiguous.
So it is not a stocking pattern. It's not symmetrical.
No. Imagine a patient who comes in with a wrist drop on the right hand.
The radial nerve is out.
Right, and a foot drop on the left foot.
So the peroneal nerve is out on the other side of the body.
Yeah.
Totally random locations.
That's mononeuritis multiplex.
What on earth causes that? That feels like a sniper taking out specific targets one by one.
That is a great metaphor. And the sniper is usually vasculitis.
Inflammation of the blood vessels.
Exactly. People forget that nerves have their own blood supply, the vasa nervorum. If a systemic vasculitis clogs one of those tiny little arteries feeding the radial nerve, that segment of the nerve dies. It has an infarct, a stroke.
And if another clot happens in a vessel in the leg?
That nerve dies.
Yeah.
It's a series of little strokes happening to random peripheral nerves.
That is fascinating. So if you see a patient with random nerves failing in different parts of the body, you have to think about a systemic disease like vasculitis.
Always. It's a huge red flag.
And then the third pattern is the big one, coloneuropathy. This is the symmetric ascending one we just talked about with the dying back axonal degeneration.
Right. Starts in the feet, moves up. Bilateral. Symmetrical. This is usually the result of a systemic process, something metabolic or toxic. And unfortunately, diabetes mellitus is the king here.
Let's dive into that. Metabolic and toxic neuropathies. Diabetes is what the most common cause of peripheral neuropathy in the Western world.
By a long shot. And the reason sugar hurts nerves is a multi-pronged attack. It's not just one thing.
Okay, what's the first line of attack?
First, hyperglycemia, high blood sugar, leads to the formation of AGE's advanced glycation end products.
AGES.
Yes. Essentially, proteins and lipids throughout the body get sugar-coated. They get, for lack of a better word, caramelized, and that makes them sticky and dysfunctional. They gum up the works.
So sticky proteins are messing up normal cell function. What else?
Then you have the polyol pathway. In states of high glucose, some cells shunt that excess glucose down a pathway that converts it to sorbitol.
Sorbitol.
And sorbitol is osmotically active. It pulls water into the cell. So the nerve cell and the Schwann cell swell up, which messes up their electrolyte balance and causes oxidative stress.
So the nerve is swollen and sticky.
And crucially, diabetes is a disease of small blood vessels. It causes microvascular damage. The walls of the vasa nervorum thicken, the lumen narrows, and oxygen delivery to the nerve drops.
So the nerve is being poisoned by sugar, swollen by water, and starved of oxygen all at the same time.
Exactly. It's a triple threat. And because the longest axons have the highest metabolic demand, they die first. Hence, the feet.
Underwood emphasizes a really important clinical point here. It's that the loss of pain sensation is the real danger.
It's the critical danger. Pain is a gift. It's a protective mechanism.
Because if you can't feel the pebble in your shoe...
If you walk on it all day long, you get a blister, you don't feel the blister, it breaks open and becomes an ulcer. The blood flow is already bad because of the vascular disease, so it doesn't heal. It gets infected.
And the infection can spread to the bone.
Osteomyelitis. And that can lead to gangrene and ultimately amputation.
It's a truly tragic cascade that starts, fundamentally, with the death of a single sensory nerve. It really highlights why diabetic foot care is so incredibly critical.
Absolutely.
Okay, moving from metabolic to inflammatory. The immune system going rogue.
And the big one here, the one everyone thinks of, is Guillain-Barré syndrome, or GBS.
This is the terrifying one. You hear these stories of people who get a simple stomach bug, and 2 weeks later they're in the ICU, unable to move their legs.
That's the classic narrative. It's an acute, often life-threatening, ascending paralysis, and it frequently follows a respiratory or GI infection.
Campylobacter jejuni from undercooked chicken is a notorious trigger.
That's a textbook one, but also Zika virus, HIV, cytomegalovirus, or even COVID-19 have been implicated.
So what is the mechanism? Why does a stomach bug make you paralyzed?
It's a classic case of molecular mimicry, a case of mistaken identity.
Friendly fire.
Exactly. The bacteria or virus has proteins on its surface that look suspiciously like the proteins on your myelin sheaths. So your immune system revs up to kill the infection. It creates antibodies. It clears the bug. But those antibodies are still circulating.
And they're looking for a fight. They spot the nerves.
And they say, hey, you look like the enemy. And they attack. Macrophages invade the nerve roots and peripheral nerves and physically strip the myelin off the axons.
It's a demyelinating process.
An acute inflammatory demyelinating polyradiculoneuropathy. Radiculo means it affects the nerve roots as they exit the spine, which is a key feature.
And the paralysis travels upwards.
Yes, toes to nose. It ascends. The real danger is when it hits the diaphragm and the intercostal muscles.
Respiratory failure.
That's the life-threatening part. That's when the patient needs to be on a ventilator to breathe for them.
But there is good news with GBS. There's hope.
There is. Remember, this is usually a pure segmental demyelination. The wire is often spared. If we can support the patient, keep them alive, support their breathing, and maybe filter out the bad antibodies with plasmapheresis,
The attack stops.
the attack stops. And that's where the continuity theme comes back in. As long as the wire isn't cut, we can fix the insulation.
The Schwann cells are just waiting to get back to work.
Precisely. They will remyelinate those bare axons. Recovery can be long and difficult, but because the underlying structure is intact, it is possible.
Now imagine GBS that doesn't get better. A version that smolders on for months or years.
That is CIDP, chronic inflammatory demyelinating polyradicular neuropathy.
Another mouthful.
Think of it as the chronic cousin of GBS. By definition, it lasts more than 8 weeks. It can relapse and remit or be slowly progressive.
So the immune system just keeps attacking, and the Schwann cells just keep trying to repair.
Over and over and over again.
And that's where we get the visual clue we talked about earlier.
The onion bulbs. The layers of Schwann cell processes wrapping the axon are the scar tissue of this chronic battle. It's the physical evidence of repeated demyelination and remyelination.
I love how these visual clues in the histology tie back to the story of the disease. Let's touch briefly on hereditary neuropathies, Charcot-Marie-Tooth.
CMT. It's actually the most common inherited neurological disorder, though many people haven't heard of it.
And this is a problem with the blueprint, right? A genetic defect.
Exactly, a defect in one of the genes that codes for the structural proteins that build either the myelin or the axon itself.
Robbins mentions a specific gene for the most common type, CMT1, PMP22.
Yes. In CMT type 1A, there is a duplication of the PMP22 gene, peripheral myelin protein 22. It's like having a blueprint that demands you put too many bricks in the wall. The structure becomes unstable and the myelin fails over time.
It's a slow, progressive demyelination.
Right. And physically, what do we see in these patients over years?
We see distal muscle atrophy. The muscles in the lower leg and the hands wither away because the nerves aren't working well.
Which gives the legs that classic inverted champagne bottle look, skinny calves below normal thighs, and they get high arches in the feet called pescavus and hammer toes.
But here's a cool Robbins detail. Sometimes the nerves are so hypertrophied from all that chronic onion bulb formation that you can actually feel them through the skin.
Palpable nerves. That is wild. The greater auricular nerve in the neck is a classic one to check. You can feel this thickened, scarred nerve cord. It connects the microscopic pathology directly to the physical exam.
All right, we've covered the wires. We've seen them cut, stripped, starved, and genetically flawed. Now we have to cross the gap.
Part 3, neuromuscular junction disorders.
The relay station.
Exactly. This is where the electrical signal of the nerve has to be converted into a chemical signal to jump across the synaptic cleft to the muscle.
And the chemical messenger here is acetylcholine.
Correct. The nerve terminal releases acetylcholine, or AG. It swims across that tiny gap and binds to an AC receptor on the muscle membrane.
And that binding opens a gate, an ion channel. Electricity flows into the muscle and the muscle contracts.
It's an elegant and incredibly reliable system until it isn't.
So the pathology here is functional. The wire is fine. The engine is fine. But the signal is getting lost in translation.
Let's start with the most famous one, myasthenia gravis.
The name itself means Gray's muscle weakness.
It's an autoimmune disease. But here, the body makes antibodies against the postsynaptic acetylcholine receptors.
So the messenger is sent. The nerve releases the ACH just fine, but the mailbox on the other side is either blocked or destroyed.
A perfect analogy. The immune system has destroyed the mailboxes. The muscle simply can't hear the nerve's command, no matter how loudly the nerve shouts.
And the clinical signature is fatigability, right? Weakness that gets worse with use.
Yes. This is crucial to understand. When you first wake up, or after you rest, the nerve can release a big burst of ACH, and there's enough to find the few remaining functional receptors. You can get by.
But as you use the muscle over and over,
the amount of neurotransmitter released with each impulse drops slightly, which is normal. It's called synaptic fatigue. But because you have so few receptors to begin with, the signal quickly fails to reach the threshold for contraction.
So the more you do, the weaker you get.
Worsens with use, improves with rest. That is the absolute mantra for myasthenia gravis.
And where do we typically see this first?
In the small, busy muscles that are used constantly, the eyelids. Patients get ptysis droopy eyelids, or diplopia double vision because the extraocular muscles aren't working together in sync.
And there is a very strong and somewhat strange link to the thymus gland.
Yes. The thymus, which sits in the chest, is like the school where T cells learn to distinguish self from non-self. In about 65% of myasthenia patients, the thymus is hyperplastic. It's overactive. And in another 15%, there is a tumor of the thymus called a thymoma.
So it seems the thymus is miseducating the immune system, teaching it to attack the AC receptors.
That's the theory. And it's why removing the thymus, a thymectomy, can often help or even cure the disease.
Okay, now let's flip the coin. Let's talk about Lambert-Eaton myasthenic syndrome.
This is a fascinating contrast to myasthenia. In Lambert-Eaton, the antibodies attack the presynaptic voltage-gated calcium channels on the nerve terminal itself.
So the problem isn't the mailbox, it's the sender. The mail is stuck in the post office.
Right. In order for the nerve to release acetylcholine, it needs an influx of calcium to trigger the vesicles to fuse with the membrane. The antibodies in Lambert-Eaton block those calcium channels.
So the nerve fires its electrical signal, but the chemical messenger never leaves the building.
Exactly. But the clinical pattern is weirdly, almost paradoxically, the opposite of myasthenia.
It is. In Lambert-Eaton, weakness improves with repetitive use. How does that work? If the channels are blocked, they're blocked.
It's a probability game. With a single nerve impulse, not enough calcium gets in to trigger release. But if you fire the nerve rapidly, over and over like revving an engine, that tiny bit of calcium that manages to sneak in with each impulse starts to build up. It accumulates inside the nerve terminal.
Until it finally reaches the threshold.
Exactly. It reaches a critical mass and boom, you get a big release of neurotransmitter and the muscle contracts.
You have to warm up the car to get it going.
That's a great way to put it. And unlike myasthenia, which is linked to the thymus, Lambert-Eaton is very often a paraneoplastic syndrome.
Meaning it's a side effect of a cancer somewhere else in the body?
Yes, most commonly small cell lung cancer. The tumor cells themselves express these calcium channels on their surface.
So the body is trying to attack the cancer.
The immune system makes antibodies to attack the tumor, but those antibodies then cross-react with the identical calcium channels on your own nerve terminals. It's another tragic case of mistaken identity.
Biology is messy.
It really, really is.
Okay, we've crossed the gap. We are finally at the engine itself. Part 4. Skeletal muscle pathology.
The meat of the matter, literally.
So for a pathologist looking at a muscle biopsy from a weak patient, the first big challenge is figuring out, is this muscle weak because the muscle itself is sick, which is a myopathy?
Or is it weak because its nerve supply is sick, which is a neurogenic process? This is the great divide. And the biopsy gives us the answer, but you have to know how to read the patterns.
So let's start with normal. What does healthy muscle look like?
Normal muscle looks like a beautiful checkerboard. You have type I fibers, which are the slow twitch endurance aerobic fibers. They stain light on some stains. And type 2 fibers, the fast twitch, power, anaerobic fibers, they stain dark.
And in a healthy muscle, they're mixed randomly, a fine mosaic. Light, dark, light, dark.
A perfect checkerboard.
So what does neurogenic change look like? What happens when the nerve is failing?
Okay, so an axon dies. The handful of muscle fibers it was connected to are now orphans. They lose their trophic support from the nerve and they start to shrivel. They become angular and atrophic. On the slide, they look like small, swished, dark fibers.
But the body tries to fix this too, that theme of plasticity again.
It does. A surviving, healthy nerve axon nearby will sense the denervated fibers and say, hey, I'll take you in. It sends out a sprout and reinnervates those orphan fibers.
It adopts them.
It adopts them. But here's the crucial catch. The nerve determines the fiber type. If a type I nerve adopts a former type 2 fiber, that fiber transforms into a type I fiber. It changes its identity to match its new parent nerve.
So the checkerboard disappears.
Exactly. All the adopted children take on the family name. So instead of a fine checkerboard, you get type grouping. Big blocks of all type I fibers next to big blocks of all type 2 fibers.
So if you see a biopsy that looks like a dashboard with giant blocks of black and white instead of a fine mix, you know that muscle has a history. It has lost its nerve and been reinnervated.
It's like a geological record of the injury written in the muscle itself.
And what happens if that big adopting nerve eventually dies?
Then you get grouped atrophy. A whole battalion of fibers, that whole block of one type, shrivels and dies together. This is what we see in diseases like spinal muscular atrophy, SMA.
The floppy infant disease.
Yes, a genetic loss of the anterior horn cells, the motor neuron cell bodies, due to a mutation in the SMN1 gene. No nerves, no signal, massive grouped atrophy.
Okay, that's neurogenic, crystal clear. Now, what about myopathic change? When the muscle itself is the problem.
In a myopathy, the nerve is shouting, but the engine is broken. We see a triad of features. First, segmental necrosis. The muscle fiber itself is literally rotting and dying, often with phagocytes inside it, cleaning up the
And we
mess.
also see regeneration, right?
Yes. The muscle stem cells, which are called satellite cells, get activated and try to build new fibers. These new regenerating fibers look blue or basophilic on the standard H&E stain.
And the third feature.
Look at the nuclei. Normally, in a mature muscle fiber, the nuclei are pushed right to the edge, to the periphery, out of the way of the contractile proteins.
Right, they're on the side.
If you see nuclei that have moved into the center of the fiber, that is a huge sign of injury and repair. Internal nuclei are a classic hallmark of myopathy.
And clinically, the lab test we measure is creatine kinase, or CK.
Right, CK is an enzyme that lives inside the muscle cell. If the cell wall, the sarcolemma, bursts open due to necrosis, CK leaks out into the blood, so a very high CK level means muscle cells are actively dying.
Let's talk about the most famous structural failure, the muscular dystrophies, specifically Duchenne.
Duchenne muscular dystrophy, DMD. It's an X-linked disorder, so it primarily affects boys. And it's caused by a mutation in the dystrophin gene.
What is dystrophin? I always think of it as a shock absorber or an anchor.
That's a perfect image. Dystrophin is a massive protein that forms a critical link. It connects the internal cytoskeleton of the muscle cell, the actin, to a complex of proteins in the cell membrane, which in turn connects to the external connective tissue matrix.
So it holds the entire structure together during the violence of contraction.
Exactly, without it.
Every single time the muscle contracts, the membrane tears.
The engine literally shakes itself apart.
It does.
Calcium rushes in through those tears, and calcium in high concentrations inside the cell is toxic. It activates proteases and triggers a cascade that leads to necrosis. The muscle cell dies.
But when you look at these young boys, they often have these huge, muscular-looking calves. Robbins calls it pseudohypertrophy.
It's a cruel illusion. The muscle looks big, but it's not muscle. The dead and dying muscle fibers have been progressively replaced by fat and connective tissue. It's weak, scar-filled tissue masquerading as strong muscle.
And the progression of the disease.
It's relentless. The satellite cells, the repair mechanisms, try to keep up for a while, but they eventually get exhausted. The boys are usually in a wheelchair by childhood, and death typically occurs in young adulthood from respiratory or cardiac failure, because the heart is a muscle too.
And Becker muscular dystrophy is the milder version.
Yes. The key difference is the type of mutation. In Duchenne, it's usually a frame-shift mutation that leads to no functional dystrophin being made at all. In Becker, the mutation allows for a truncated or partially functional dystrophin to be made.
So it's the difference between having no anchor at all and having a rusty, shorter anchor chain. It works, but not well.
Exactly. So the disease is much slower and more variable.
Okay, let's shift to inflammatory myopathies. Autoimmune attack on the muscle.
And the first one is dermatomyositis. This one is distinct because it doesn't just attack the muscle, it attacks the blood vessels that feed the muscle.
The microvasculature. It's a vasculopathy first.
Yes. Antibodies and complement get deposited in the walls of the capillaries in the perimysium, the connective tissue around the muscle bundles. And this creates a very specific and diagnostic histologic pattern. Perifascicular atrophy.
Break that down for us. Perifascicular.
A fascicle is a bundle of muscle fibers. The blood supply enters from the outside of the bundle. If the capillaries are attacked and damaged, the muscle fibers on the edge of the bundle, the periphery of the fascicle starve for oxygen first and atrophy.
So the center of the bundle looks relatively okay, but there's a ring of shriveled fibers around the outside.
Exactly. It's diagnostic gold. And clinically, you see the dermatopart, the skin changes, the heliotrope rash, a purplish rash on the eyelids, and Gottron papules, which are scaly bumps over the knuckles.
And what about polymyositis?
Polymyositis is classically taught as a direct T-cell attack on the muscle fibers themselves. CD8-positive cytotoxic T-cells invade the fibers and kill them. But honestly, the diagnosis is made much less frequently now. Many cases that were once called polymyositis are being reclassified. It's becoming a diagnosis of exclusion.
The one that isn't a diagnosis of exclusion, and is very important, is inclusion body myositis, or IBM.
This is the one to remember for older adults. If a patient over the age of 50 presents with slow progressive weakness, especially weakness that affects the finger flexors and the quadriceps, you have to think about IBM.
And the biopsy shows something very specific and strange.
It does. It shows rimmed vacuoles. You see these empty-looking spaces, or vacuoles, inside the muscle cell that have a granular reddish rim on a trichrome stain. And inside these vacuoles, you find protein aggregates, things like amyloid and tau.
Tau. as in the same protein that accumulates in Alzheimer's disease.
Exactly. It's almost like a neurodegenerative disease happening inside the muscle cell. And unlike dermatomyositis, it does not respond well to steroids or immunosuppression. That's a vital clinical distinction.
Finally, let's quickly touch on metabolic and toxic myopathies.
A classic one is mitochondrial myopathy. The mitochondria are the power plants of the cell. If they're genetically faulty, the cell is chronically starved for energy.
How does that look under the microscope?
The cell tries to compensate by making more and more abnormal mitochondria. They pile up under the cell membrane. On a special stain called a Gamori trichrome, they look like ragged red fibers. The contour of the fiber looks rough and intensely red at the edges.
And this often has maternal inheritance pattern, right? Because we get our mitochondria from our mother's egg.
Correct. And for toxic myopathies, we have to mention statins.
The cholesterol-lowering drugs. So many people are on them.
And they are very safe for the most part, but they can cause muscle pain and rarely actual necrosis. Usually it stops when you stop the drug. But in very rare cases, they can trigger a self-perpetuating autoimmune necrotizing myopathy that keeps going even after the drug is withdrawn.
Okay, part 5. We can't leave without a quick word on tumors. Not common, but important.
Peripheral nerve sheath tumors. Two main benign players to distinguish.
Schwannoma versus neurofibroma, they sound similar.
They do, but they are very different beasts. Schwannoma is a benign tumor of the Schwann cells. It grows as a nice encapsulated ball, and crucially, it pushes the actual nerve fibers of the nerve to the side.
So a surgeon can often see the nerve stretched over the surface of the tumor and carefully peel it off?
Usually, yes. You can dissect the tumor away from the nerve without having to cut the nerve. It's an eccentric mass.
And a neurofibroma.
That's the messy one. It grows within the nerve fascicles. The tumor cells, the collagen, the axons are all tangled up together like a bowl of spaghetti. It's not encapsulated. It infiltrates the nerve.
So you can't just peel it off?
No. To remove the tumor, you often have to sacrifice that segment of the nerve. That's the key surgical difference.
And they're strongly associated with the neurofibromatosis syndromes,
Right.
NF2 for schwannomas.
And NF1 for neurofibromas, and you have to keep an eye on the plexiform neurofibromas in NF1 patients, because those have a risk of transforming into a malignant peripheral nerve sheath tumor, an MPNST, which is a very aggressive sarcoma.
All right, we have covered an immense amount of ground. We've gone from the single Schwann cell all the way to the geometry of muscle bundle. Let's synthesize this. Let's bring it all back.
It really comes back to your opening words. Continuity and energy.
The chain of command.
The chain. Movement fails if the axon is cut, which is Wallerian degeneration. It fails if the insulation is stripped, like in GBS or CMT.
It fails if the reception is blocked at the synapse, like in myasthenia.
Or it fails if the structural integrity of the engine, the muscle, is compromised, like in Duchenne muscular dystrophy.
And the so what for the clinician, for the student trying to learn this?
Understanding which failure it is changes everything. If a patient comes to me with weakness, I need to know, is this neurogenic or myopathic? Is it axonal or demyelinating?
Because the treatment is completely different.
Completely. If it's myasthenia gravis, I'm thinking about immune suppression. If it's diabetic neuropathy, I'm focusing on tight glucose control. If it's Duchenne, I'm looking at genetic counseling and supportive care. The pathology dictates the therapy.
I want to end with a thought that really struck me while reading Underwood for this. It's this constant battle in these diseases between plasticity and permanence.
Go on.
The peripheral nervous system is so optimistic it wants to regenerate. The Schwann cells make their Bugner bands. The axon sprouts at a millimeter a day. The muscle has its satellite cells, desperately trying to repair the damage in a dystrophy. There's this incredible innate drive to fix things.
But there's always a but.
But there is a tipping point. In chronic disease, chronic inflammation, chronic dystrophy, chronic denervation, the repair mechanisms get exhausted. The fibroblast, the cell that makes scar tissue, takes over. That's the fatty replacement we talked about in Duchenne.
Exactly. Once muscle or nerve is replaced by fat and fibrous scar tissue, the game is over. That is permanent. That structure and function is lost forever.
So the entire clinical battle, everything doctors do, is really about buying time.
It's about buying time. It's about stopping the damage before that incredible plasticity gives way to permanence. Before the onion bulb isn't a sign of a valiant fight anymore, but it becomes a tombstone.
That is a powerful way to look at it. We are racing against the scar tissue.
In so many of these diseases, we are.
Well, on that note, I highly recommend you open up Robbins to chapter 27. Find the diagram of type grouping versus the normal checkerboard. It's one thing to hear us describe it, it's another to see that history of a nerve injury written in the tissue itself.
It really brings the whole story to life. It's pathology as a narrative.
Thanks for diving deep with us. Keep those wires connected and those engines running. We'll see you next time.
Stay curious.